You are about to see how the weather affects our planet over a complete year. It's the 1st of March, 2019, the beginning of a meteorological spring in the Northern Hemisphere. Let's start the playback. Every 2 seconds marks a day, another complete rotation of the Earth. At this time of year, tropical cyclones form in the southwest Indian Ocean. This one is called Cyclone Idai. It will turn out to be the second deadliest ever recorded in the southern hemisphere. Over 1,000 people across East Africa will lose their lives. This year, the temperature distribution of the Indian Ocean is uneven. The eastern side is unusually cool, and the western side is unusually warm. This warmer water contributes to Cyclone Idai's record strength, and Africa will have increased rainfall throughout the year. On the other side of the ocean, where the water is cooler than normal, there will be drought. Let's jump to May and look at North America. At this time of year, a flow of warm, humid air heading north clashes with another flow of cool, dry air heading south. Where they meet, supercell storms begin to form. These intense thunderstorms can generate narrow, violently rotating columns of air known as tornadoes, which can achieve the highest measured wind speeds on Earth. Sometimes over 400 kilometers per hour. Further north, you can just see the smoke from huge wildfires in Alberta, Canada. Dry, windy conditions are helping them to spread to a much larger area than normal. As the year advances, the point where the sun is directly overhead at midday has been shifting northwards due to the tilt of the planet. It has reached its northernmost position at the Tropic of Cancer. On that imaginary line lies India, and the direct sunlight is contributing to an intense heatwave there. But it's not just near the equator that's affected by high temperatures. Near the Arctic, it is much warmer than usual, and in Siberia, an area the size of Belgium is on fire. Europe is now experiencing a heatwave as well, and hundreds of people will succumb to the record high temperatures in the next few days. The European heatwave in 2022 will be the deadliest weather event worldwide that year. Meanwhile, back in India, monsoon rains arrive. They form every year when a difference in heating over land and ocean causes a change in the wind direction. They're later than usual, but the most intense in 25 years, fueled by the same warm water that's linked to the increased rainfall in Africa. Over in South America, fires in the Amazon rainforest, which have been burning for much of the year, now reach their peak. They started intentionally to clear land for agriculture, but high temperatures have dried out the vegetation, allowing the fires to burn more intensely and spread more quickly. They appear in much greater numbers this year than normal. As summer progresses in the Northern Hemisphere, the Atlantic Ocean has been warming up. Conditions are now perfect for the formation of tropical cyclones, such as this one, Hurricane Dorian. It's just made landfall in the Bahamas and is about to become the region's worst natural disaster on record. The damage is catastrophic. At least 70,000 people are left homeless, 84 people lose their lives, and over 200 are missing. Dorian begins to fade and tracks up the coast of the eastern United States. Air currents will transfer that heat and moisture all the way to the Arctic Circle. The Arctic is particularly affected by rising temperatures. On this day, the amount of Arctic sea ice is the second lowest since satellite records began in the 1970s. Back in the Atlantic Ocean, not all hurricanes head towards North America. This one, Hurricane Lorenzo, is traveling towards Europe, and it's the most easterly tracking Category 5 hurricane on record. By the time it reaches the cooler waters around the British Isles, much of its strength is gone. But as the climate changes, will that always be the case? On the other side of the planet, another tropical cyclone called Typhoon Hagibis is also traveling further than usual. As it hits Japan in time for the Rugby World Cup, it is one of the strongest typhoons on record and will become one of the costliest. Further south, Australia has been experiencing months of drought. It is on the cooler eastern side of the Indian Ocean, where rainfall is reduced. Record high air temperatures have made things even worse. Bushfires are already widespread throughout Australia and now in December reach their peak. The fires are having a major impact on the area's ecology. Billions of animals have lost their lives, and many areas will take years to recover. Today, on the other side of the world, a Boeing 747 makes a record-breaking transatlantic flight, New York to London, in just 4 hours, 56 minutes. This incredible feat has been helped by a strong jet stream, acting as a powerful tailwind. This high-level current of air is far stronger than usual and is also sending a conveyor belt of storms towards Europe. They hit, one after the other, making it the wettest February on record in the British Isles. That brings us to the end of our eventful year of weather for planet Earth. Another year of extremes affected by rising temperatures. 2019 was the second warmest year on record, and 2020 will go on to be even warmer. Every year, the seasons bring regular changes to weather patterns across the planet, but there are other naturally occurring patterns that, whilst not as regular, can still have major impacts on people's lives. They can occur over periods of time, ranging from months to decades. Climate Station's weather year coincided with one of these, a fluctuation in sea surface temperatures called the Indian Ocean Dipole, and that happened to be one of the strongest on record. The Western Indian Ocean became much warmer than usual. The extra evaporation caused extreme rainfall in that area. This led to flooding in East Africa that affected nearly 3 million people. Meanwhile, the waters on the eastern side dramatically cooled, causing parts of Australia to become drier and warmer than usual, exacerbating devastating bushfires. This behaviour can sometimes reverse too, often with flooding in Australia and Indonesia and drought in Africa. Another fluctuation has an even greater effect than the Indian Ocean Dipole. In fact, it can be strong enough to affect the temperature of the entire planet. It's called the El Niño Southern Oscillation, or ENSO for short. This time, it's the surface waters of the tropical Eastern Pacific Ocean that become warm, which can have a major impact on marine life. In 1998, El Niño caused the first recorded global coral bleaching event. When the behavior is reversed, referred to as La Niña, there can be strong cold outbreaks in North America, flooding in Australia, and increased hurricane activity in the Atlantic. Ocean currents form a giant circulation system around the planet, transferring heat from the equator to the poles. The Gulf Stream is one of the largest and fastest. It starts when winds near the equator drive surface water northwest to the Gulf of Mexico, where it dramatically heats up. This warm water is then pulled across the Atlantic towards Europe by westerly winds, where it releases an enormous amount of heat and moisture into the colder atmosphere. The freezing air in the North Atlantic cools the water, and as ice forms, cold, salty, dense water is left behind. This is so heavy, it sinks to several kilometers below the surface in the largest undersea waterfall in the world. This helps to drive global ocean circulation, drawing surface waters from the south. In turn, this increases the Gulf Stream flow, returning cold water deep under the surface to the south to complete the circuit. Without the Gulf Stream, the temperature in Europe would be at least 5 to 10 degrees Celsius lower, much closer to many regions at the same latitude that are far colder. Climate models suggest that as the climate warms, the water in high latitudes will become warmer and less salty, leading to less sinking and a weakening of the circulation. Some studies have suggested that this slowdown could happen abruptly, with serious impacts on regional climate and weather around the world. Our atmosphere is always on the move. It's constantly flowing from one place to another. Across the planet, continuous cycles of rising and sinking columns of air help to create our weather and define the type of climate in each part of the world. But what causes these air currents? They fundamentally rely on the land and ocean that's near the equator, receiving more direct sunlight and becoming warmer than places further away. Hot air rises, and this helps lift water vapor evaporating from oceans into the atmosphere. As it cools, the water vapor condenses to form clouds. These can grow to become showers or thunderstorms, which can be seen on our satellite video as a near-continuous line of cloud encircling the Earth near the equator. They form when northeast trade winds from the northern hemisphere meet southeast trade winds from the southern hemisphere. As the Earth orbits the Sun through the year, the pole that's tilted towards the Sun alternates, in turn warming one hemisphere more than the other. This creates our seasons and shifts the line of showers and thunderstorms north and south, changing the air currents to help generate seasonal monsoons and tropical cyclones. High at the top of the atmosphere, the cooler air heads away from the equator north and south, where eventually it sinks back down to Earth. This sinking air leads to much drier and calmer weather in these zones, and this is where the deserts form. The air then heads back to the equator to complete the circulation. Air current circulations don't just exist here, but in every location, driving weather systems across the planet, all part of a continuous global circulation. As the Earth rotates, air within the atmosphere is deflected east to west by what's called the Coriolis force. This is crucial for driving the easterly trade winds near the equator and affects the paths of monsoons and tropical storms. The Earth's rotation also plays a crucial role in driving fast-moving ribbons of air high up in the atmosphere called jet streams. The temperature contrast between the warm and cool zones helps to give them their strength. Jet streams act as conveyor belts, carrying weather systems around the planet. Sometimes, factors such as a reduction in the temperature difference between the air masses can weaken the jet stream, causing its shape to buckle and stall, becoming stuck in one place. Regions can then experience the same weather for long periods of time. This causes rainfall to accumulate, leading to flooding or prolonged dry spells, generating drought. It's likely that as the planet warms, the nature of jet streams will change, which could have dramatic impacts on local weather and climate. These changes could also potentially lead to extreme floods and droughts happening more often in the future. Jet stream behavior is an important area of current climate research. As the atmosphere and oceans continue to warm, the behavior of other air currents is likely to change too, which could have a dramatic effect on our future weather. In the middle of the last century, few people were interested in climate change. Levels of greenhouse gases in the atmosphere were unknown. Temperatures were being recorded, but no one was assembling them to make an accurate global picture. At this time, a young researcher called Charles Keeling was working out a way to measure the level of carbon dioxide in the atmosphere. He found concrete proof that as the level went up and down with the seasons, it was also steadily rising. A few scientists had already said this was likely. Burning fossil fuels rapidly releases millions of years of stored carbon back into the atmosphere. And it was concerning. As a greenhouse gas, carbon dioxide acts like a blanket that traps the heat, so it causes the whole planet to warm up. Fast forward to the present day. We now have a complete picture of how much carbon dioxide has risen in the atmosphere. The level is still rising, and in 2021, it had increased by an astonishing 50% since humans embarked on the Industrial Revolution. But it's the rate of change which is most concerning. Over the last 120 years, other major factors that could influence global temperature have had negligible impact. Factors such as the amount of energy from the sun or the amount of dust from volcanic eruptions that would block the sun's energy from getting through. So, we know that rising levels of greenhouse gases have been the main influence on the climate over the last 120 years. But how much have they affected the temperature of the planet? Years of records from all over the world have now been brought together to give us a picture of how the overall global temperature has changed over time. As expected, it's risen. The temperature is now far higher than it was a century ago, but it's the rapid rate of warming that has been most concerning. The true effect has been masked, though, because 90% of the extra heat has been absorbed by the oceans. Since 1955, we've been able to monitor this too. Over many years, the heat will gradually be released again back into the atmosphere. Even if levels of greenhouse gases can be reduced, unfortunately, this heat will keep global temperatures higher than they otherwise would have been. So far, we've looked at the overall effects, but let's now see how temperatures have changed in various locations across the planet. Let's start in 1901 and run through the years to the present day. The pins show the difference in temperature relative to the middle of the 20th century. Blue pins are cooler. Red pins are warmer. The longer the pins, the greater the difference. Watch how the cooler blue areas gradually disappear, and then the warmer red pins take over as the planet warms up. You can see how the warming has accelerated, particularly in recent years, and some areas have warmed more than others, especially the Arctic. This Arctic warming has had major consequences. Since 1979, satellites have been able to monitor sea ice, and the amount in the Arctic has reduced dramatically. Ice is good at reflecting heat back into space, so the reduction has caused the ice-free ocean to absorb even more heat than it previously would have, causing yet more warming. If we look at the temperature records for Svalbard within the Arctic Circle, the rise has been particularly noticeable in recent years. This has led to the glaciers there dramatically reducing in volume. This shows how the glaciers were in 1936, and this is what they're like now. The red areas highlight how much ice has melted away. But it's not just at this location. In only the last 40 years, the average thickness of the world's glaciers has reduced by 24 meters, the height of an 8-story building. ice sheets are reducing too. We've only been accurately monitoring these since the 1990s, but in that time, Greenland alone has lost nearly 5,000 gigatons of ice. When melted, that's almost double the volume of Lake Victoria in Africa. All the meltwater from land-based ice sheets and glaciers flows into the oceans, causing the sea level to rise. This is made worse by the ocean waters expanding in size as they warm. This graph shows the global rise in sea level over the last 120 years. Half the increase has happened since the early 90s. As with temperatures, some areas are affected much more than others. Some low-lying areas are already under threat. It is difficult to prove that specific weather events are caused by climate change. But we do know we have seen more extremes as the planet warms. There's been an increase in heat waves, with many temperature records being broken. Changes in rainfall patterns have led to more frequent and severe weather events at either end of the scale, from droughts to floods. The past 9 years were the warmest on record globally. When Keeling first made his discovery, we had little evidence of climate change, but as each year goes by, we gather more data showing how much the climate is changing. Have you ever wondered if climate change is affecting where you live? In the observations section of Climate Station, you can find out. You can select a location close to your home on the globe and look up all the temperature data. Let's say we wanted to look up the temperature for this location. We can select it on the globe, pick a recent year, and see the average temperatures for every month. But how does that differ from the temperatures in the past? We need something to compare against. We use what's called a reference climate. This is the average temperature over a 30-year period of time. We could choose any 30-year period as our reference, but Climate Station uses 1961 to 1990, a period often used by climate researchers that lies within the middle years of our dataset. On the globe, we can represent areas cooler than this climate with blue pins and warmer areas with red pins. The longer the pins are, the bigger the change is. For our chosen location, we can now plot a graph showing how temperatures differed from the reference climate over the years. But now let's compare it with what's been happening inside the Arctic Circle. In this part of the world, the change has been dramatic, particularly in recent years. But we can go one step further. We can compare what's been happening to the warmest summer months and the coolest winter months for each year. Let's select the warmest months. This graph suggests that the temperatures in summer haven't been rising quite as dramatically. Now let's have a look at the coolest months. The change is far more noticeable, indicating that not only are the overall temperatures rising, but the coolest months are getting warmer here more than the warmest months. On the globe so far, we've only been able to look at 1 year at a time. But if we take a 10-year average, we get a much better idea of the overall trend. Here are the 10 years from 1901 to 1910. Now let's jump to the last 10 years. Switching between the two, we can really see how much the climate has changed over the last 120 years, particularly in the Arctic regions. The Earth's atmosphere contains 78% nitrogen and 21% oxygen. The other 1% is made up of greenhouse gases, such as water vapor, carbon dioxide, methane, and nitrous oxide. That tiny 1% is crucial for regulating our climate. Without greenhouse gases, the Earth would be far too cold to live on. They act like a blanket, keeping the planet warm. As with the glass in a greenhouse, they help to trap the heat from the sun that would otherwise radiate back into space. So why do we want to get rid of them? Because human activity is rapidly increasing the levels of greenhouse gases in the atmosphere. This is heating the planet beyond the level that many plants and animals are accustomed to, and faster than they can adapt. This shows all the main contributions humans make to our climate, representing both warming and cooling effects. The main greenhouse gases are highlighted, with carbon dioxide having the largest warming impact. Since parts of the world became industrialized, the level of carbon dioxide in the atmosphere has increased by a staggering 50%, and the increase is accelerating. By using methods such as analyzing samples from the bottom of the ocean, we now know the level hasn't been this high for at least 2 million years. It would be even higher if some of the extra carbon dioxide hadn't been absorbed by the land surface and oceans. Methane is the second highest contributor. There's around 200 times less of it in the atmosphere, but it's much more effective at trapping heat than carbon dioxide. Since pre-industrial times, its level has more than doubled. In fact, it's risen an astonishing 10% in just the last decade. By far, the most abundant greenhouse gas is actually water vapor. It's created by evaporation and removed by rain. The amount of water vapor in the atmosphere varies with atmospheric temperature. For every 1 degree Celsius of warming, the atmosphere can hold 7% more moisture. But remember that water vapor is a greenhouse gas, so that extra 7% will cause even more warming. It's a feedback loop, and this behavior amplifies the heating effect of other greenhouse gases too. When they warm the atmosphere, more water vapor can be stored, leading to even more warming. Most water vapor is invisible, but a minority forms the clouds that we see, which are particularly good at trapping heat, especially at higher altitudes. Some do reflect energy from the sun back into space, though. This offsets part of the warming. So, greenhouse gases from human activity are causing the planet to warm. But what would happen if we completely stopped emitting them? The challenge is that even if we did completely stop emitting them, the amount already emitted won't instantly disappear. So how quickly would the levels go back to how they were before we began our greenhouse gas emissions? The methane would dissipate in around 10 years, but it could take hundreds of years for the level of carbon dioxide in the atmosphere to do the same, and even longer for the oceans. If we want to stop the planet warming, ideally, we not only need to reduce our emissions, but find ways of mopping up the excess greenhouse gases that are already there. What might the rest of the century be like for our planet? As the Earth warms, the impacts of climate change become greater. Currently, the global average temperature is around 1.2 degrees Celsius higher than it was before the Industrial Revolution, and already we're beginning to see some of the effects. In 2015, most countries in the world signed the Paris Agreement, with the aim to keep the temperature below 2 degrees Celsius of warming and focus on limiting it to 1.5 degrees Celsius. Even if the temperature stays below this level, it won't solve all the issues. The 1.5 degree target has just been chosen to protect us, not as a guarantee. So, Would keeping this agreement have any benefits? Alternatively, what might the consequences be if we don't? The projection section allows us to explore the possibilities, using information taken from the best climate models we have today. The results all depend on how much greenhouse gas we release into the atmosphere. So in this section, we can choose from a range of different emission scenarios to find out what would happen. For each potential future, we can observe the change in temperature over time and the impact it would have on a variety of different factors. In many ways, it's just like the observation section, with the global trend graphs and selectable regional temperature pins. This time, however, the graphs are more suited to showing general long-term trends rather than specific years. The model simulations give us access to far more data than was observable in reality, particularly before satellites became available. So, this section contains additional information that helps us to see more of the impact both on us and the natural world. We can pull up maps showing detailed climate information and how each part of the world would be affected. These are plotted for each level of global warming, the 1.5 and 2 degrees Celsius targets, plus the nightmare scenario of reaching 4 degrees Celsius. We can look at two different types of data simultaneously to make side-by-side comparisons. We can see that some areas would become wetter, while others would face severe drought. For each emission scenario, we can also monitor a range of specific risks for the planet's climate and how quickly they would increase as we move through time. We can see that even now, warm water corals are under threat. But thankfully, at least the risk of climate tipping points, the points of no return for the planet, only increase at much higher warming levels. The calculations assume that society hasn't taken any actions to adapt to the changing climate, making the consequences as severe as possible. This is accurate for less developed parts of the world and elsewhere if change happens quickly. By reducing our greenhouse gas emissions, we can both slow down the warming of our planet and reduce the very worst long-term impacts, providing us and the natural world with more time to adapt. Climate Station has allowed us to gain a new appreciation of our planet's climate and how it's changing. The story continues to evolve. In 2023, the global temperature suddenly surged. It was warmer than any previous year ever recorded, only to be surpassed by 2024, which exceeded 1.5 degrees Celsius above pre-industrial levels for the year. Remember that most of the heat is stored in the ocean, hiding the true scale of the problem. On our current course, by the end of the century, the planet will have warmed by nearly 3 degrees since pre-industrial times. Heat waves, droughts, and heavy precipitation will become more frequent and intense. Tropical cyclones are more likely to generate devastation on the scale of Hurricane Dorian, as shown here. The consequences will affect everyone. But this doesn't have to be our future. We know what's causing the problem. Burning fossil fuels has released millions of years of stored carbon back into the atmosphere, causing it to heat up. Meanwhile, we've destroyed natural features such as peatlands and forests that would have helped to recapture this carbon. The Paris Agreement set out a goal of net zero emissions by 2050. The amount of carbon we release should be balanced by the amount we capture again. This would reduce warming by the end of the century to 1.5 degrees, far less damaging than the 3 degrees where we are currently heading. We've already come a long way and rapidly adopted green energy technologies. About 15 years ago, climate research indicated we were heading to nearer 4 to 5 degrees of warming by 2100. So, there is still hope. But hope is delivered through action, and we need to act now. We need to reduce the amount of fossil fuels we burn as much as possible, switching to renewable energy. We need to restore and expand natural features such as peatlands, forests, and seagrass to capture the carbon that we do emit. Everyone needs to play their part. This is true for us as individuals and as communities. We can encourage industries and nations to play their part too, by the choice of organizations that we support. There are 8 billion of us on the planet. It's all down to the choices we make. How we travel, how we heat our homes, and what we consume. The challenge is to ensure that as many people as possible understand the situation we're in. This is the first step towards positive change. Everyone's contribution to limit further warming will make a difference. Every fraction of a degree matters. Our introduction to Climate Station is now complete. You're now welcome to continue your journey and discover your very own climate story. Geological research using rock and ice cores shows that the Earth's average sea level has risen by over 125 meters since the middle of the last ice age, about 20,000 years ago. Sea levels have stayed almost the same for the last 8,000 years, though. But just over a century ago, they started to rise again. They have risen by over 7 centimeters in just the last 20 years alone, the same amount they increased over the previous 60 years. We've been measuring sea levels accurately with tide gauges since the 1600s, and now satellites provide far more coverage. They show that some regions have experienced a greater rise than others. In Europe and the east coast of North America, levels have risen over 3 times more than the global average. Sea level rise has a number of significant causes. For example, melting glaciers and land-based ice sheets, and the volume of oceans expanding as they've heated up. The latter occurs from a process called thermal expansion. Over time, this heat is released into the atmosphere. This means that the melting ice sheets are likely to be the main contributing factor to sea level rise in the future. Sea ice is melting too, but like an ice cube melting in a drink, it barely affects the level. Although the recent rise can be measured in centimeters rather than the meters of the distant past, it is already having an impact on low-lying coastal regions. This will be felt elsewhere in the future. Predicting sea level rise is complex, but the last time Earth's global temperature was similar to today, 125,000 years ago, the sea was at least 5 meters higher than its current level. Could this happen again as the full effects of climate change pan out? How high the sea level rises depends on how much the Earth warms. The future projections give us our best estimate of what is likely to happen this century. The temperature of the planet is rising, but in some areas it's rising much more than others. The Arctic is warming more than twice as fast as the rest of the world. It's only recently that people have begun to understand properly what's causing this polar amplification, and it seems to be a combination of several reasons. As ice and snow melt due to rising temperatures, more of the dark surface underneath is revealed. This allows the land and ocean to absorb more heat, causing yet more warming in a feedback loop. This locally exaggerates the warming caused by greenhouse gases. It's now known that other feedback loops also exist, caused by more complex factors involving how the atmosphere behaves. But currently, polar amplification seems to be happening far more in the Arctic than the Antarctic. Why might this be the case? It's thought that the ocean around the Antarctic tends to dampen the effect. For the Arctic, ocean currents carry heat from the tropics northwards, exaggerating the heating effect in the Arctic. The Antarctic ice sheets have a major effect too. They're several kilometers thick and act as a giant blanket, insulating the continent from warming effects elsewhere. Additionally, the strong surface winds found at high elevations limit the warming by redistributing cold air to coastal regions. None of these factors are present in the Arctic, and there, polar amplification is very noticeable. But does it affect the climate? Some scientists have found evidence that it can weaken the jet stream and lead to an increase in extreme weather, such as flooding and drought, but this is currently an area of active research. To predict what's likely to happen to the Earth's climate in the future, climate scientists build detailed computer simulations. These consist of a collection of mathematical models covering all possible influences on the results. Accurate recreations of how the atmosphere and oceans behave are also included. The models interact with each other, just as the Earth's natural systems would in reality. They work by calculating snapshots of the climate taking over regular time periods, progressing into the future, typically at half-hour intervals. The calculations are performed for every location on a 3D grid covering the whole planet. They require a huge amount of computer power because every grid point is affected slightly by every other one, making the calculations far slower. For simulations to give accurate projections, the scientists must include estimates for external factors, such as how much greenhouse gas will emit over time. This is impossible to predict accurately for the long term, so separate simulations are run to cover a range of future possibilities. Just as improvements in computer power over the years have led to more realistic, high-resolution video games, the same is true for climate models, which push the fastest supercomputers available to the limit. Current simulations often have grid points around 100 kilometers apart. Halving that distance would require a 10-fold increase in computer power, but the current resolution is still good enough to represent large-scale weather systems. Current weather forecasts can use resolutions of only a few kilometers or less, but they only need to predict the results for a few days ahead, rather than the decades required to predict the future climate. But how can these long-term climate projections be accurate when forecasting the weather for only a few weeks ahead is a challenge? Weather is highly complex and unstable, but this behavior tends to balance itself out over time, which allows climate models to give accurate long-term trends, even if they can't predict the specific details. For all their sophistication, how do we know these climate models actually work? Scientists often check their models by comparing calculations for the past century with the equivalent observed results. If the two are close, then scientists can be more confident that the model is reliable. What about the results of old climate models published in the past? How successful were these at predicting the climate we have now? Let's overlay some old results onto our observed global temperature data and take a look. The early models were very primitive by modern standards, but they became increasingly sophisticated as computer technology improved. The projections that you can explore in Climate Station are based on combined results from multiple climate institutions, published in the latest report from the Intergovernmental Panel on Climate Change. They convey the best estimates that we currently have on what our future climate will likely be. Eight percent of the fresh water on Earth is stored in two giant ice sheets, thousands of meters thick, covering most of the surface of Greenland and Antarctica. These were formed from snow, becoming compressed over many centuries under the remains of the last ice age, a time when ice sheets covered much of northern Europe and North America. Over time, the ice, moving under its own weight, gradually flows towards the coast. This eventually forms ice shelves that float on the ocean. These in turn carve into icebergs and melt away in the relatively warmer oceans. New snowfall helps to replace the ice, but is this sufficient to prevent the ice sheet flowing away? Measuring the overall gains and losses is important because when the water from the melting land-based ice finds its way to the ocean, it contributes to a rise in sea level. Accurate measurements taken using satellites have found that the amount of ice is steadily declining, particularly in Greenland and western Antarctica. As an ice sheet melts, its height reduces, which exposes the surface to higher temperatures at lower altitudes, causing yet more melting. This reduces the level even further in a vicious circle. Currently, this could be stopped if we halted the rise in global temperatures, but that may not always be the case. If this continues, it could lead to an irreversible decline, a climate tipping point. It is thought that for some parts of the ice sheets, This could occur soon with our current rate of warming. Preventing global sea level rise would then become an even greater challenge. In the summers of 1936 and 1938, a small scout plane flew over the Arctic islands of Svalbard, photographing the terrain. The people on board had no idea how important the images they were capturing would be in demonstrating some of the most extreme effects of climate change anywhere in the world. To them, this was just a routine survey to create a map. They didn't know that much of the ancient glacial ice that they were flying over would soon be gone forever. For many years, the photographs sat in a drawer, forgotten. It was only 80 years later that they were rediscovered, and it was realized they contained enough detail for software to reconstruct the area as an accurate 3D model. This could then be compared directly with how the same area looks today. In front of you is a small part of that model. You can compare the 1930s reconstruction with how the same area looks now. The red areas highlight how much ice has melted away. From this comparison, we now know exactly how much the glaciers of Svalbard have declined, and this chart shows the result for the whole area. The blue shows where the ice has increased, and the red where it's decreased. For at least the past 150 years, most glaciers on the planet have been slowly shrinking. But in the last 40 years, the rate of melting has dramatically accelerated. Recent findings show that now almost all of the world's glaciers are retreating simultaneously, which hasn't happened for at least 2,000 years. Summer is the crucial time for glaciers. Most of the damage is caused by longer, warmer summers, melting more ice than's being replaced by fresh winter snowfall. Polar amplification has increased the rate of warming in Arctic areas. Svalbard is particularly vulnerable because there the rate is even faster, but many other areas are also badly affected. In just the last 40 years, the average thickness of the world's glaciers has reduced by 24 meters, the height of an 8-story building. In that time, an incredible third of the volume of New Zealand's glaciers has melted away. Since 1901, melting glacial ice has been a larger contributor to sea level rise than the ice sheets of Greenland or the Antarctic. If we lost all the world's glaciers, that alone would cause a global sea level rise of 0.5 meter. Even now, devastating flash floods can occur when melting walls of glacial lakes burst, creating a deadly wall of water that can engulf villages downstream. The loss of glacial ice removes a key source of seasonal meltwater that supplies fresh water for important wildlife habitats. We rely on this water too, for drinking and many commercial activities. Unfortunately, every future scenario shows that glacial retreat will continue, but reducing the global rise in temperature will help to reduce the rate of decline. This would have a big impact on the amount of global sea level rise. Whatever happens, photography will continue to play a vital role in documenting what was once there. Carbon is vital to life on Earth. Every day, plants store carbon from carbon dioxide in the atmosphere or ocean. When plants are eaten by animals, this carbon is passed on. Both plants and animals return carbon back to the atmosphere when they release energy during respiration, and so the process is repeated. As a greenhouse gas, this carbon dioxide helps to keep the natural world warm enough for life to flourish. Over a longer time, carbon passes directly between the atmosphere, land, and ocean. The carbon-rich remains of dead plants and animals are compressed into fossil fuels, such as oil and coal, over millions of years. All these processes are more or less in balance. If left alone, the quantities of carbon stored at each stage would hardly change, but human activity disturbs this balance. When fossil fuels are burned, we release millions of years of stored carbon back into the atmosphere, carbon from the remains of forests which existed long ago. As the extra carbon is absorbed in the ocean, the water's acidity increases, and this affects marine life, dissolving their shells and skeletons. To make matters worse, we've cleared vast areas of forest that could have helped absorb the carbon dioxide again. If we continue as we are, one day the balance will settle at a new level, but the world will be a very different place. All life on Earth is part of an intricate web of species that rely on each other for survival. If any are threatened, it risks upsetting the balance, potentially also threatening our survival. Yet it's thought that 1 million species currently face extinction. Species are becoming extinct 100 times faster than in pre-human times. In the last 50 years, the thousands of populations monitored by the World Wildlife Fund have declined on average by over 69%. If this decline continues, it will have a dramatic effect on us, with loss of livelihoods and threatened food supplies. So, Is the current loss of biodiversity caused by climate change? Well, actually, the majority is caused by natural habitats being destroyed by changes in land use. But biodiversity and climate change are very closely linked. Deforestation, for example, reduces both biodiversity and the ability of the planet to absorb carbon dioxide from the atmosphere, leading to rising temperatures. These rising temperatures can lead to further biodiversity loss. A good example of this is what is currently happening to coral reefs in many parts of the world. Coral reefs are the foundation of unique ecosystems, home to many types of marine life. Corals are marine animals, similar to sea anemones and jellyfish. But unlike them, they secrete hard calcium carbonate exoskeletons that over many years grow into giant reefs. The biggest collection is the Great Barrier Reef in Australia, which is the largest structure made by living organisms. Corals typically feed off microscopic plants called algae that in turn need the corals to survive. It's the algae that give the corals their vibrant colors. In front of you is a life-size replica of a real coral reef, made using advanced photo-scanning techniques. Some of the corals are brightly colored as normal, but many here have lost their colors altogether. They are victims of what is known as coral bleaching. Rising ocean temperatures cause the algae to release toxins, and the corals have reacted by expelling them. With the algae gone, the corals turn white and often die, threatening the ecosystems that rely on them. Recently, bleaching events have become increasingly common, and corals have died on a massive scale in many parts of the world. The reef here was a victim of a major mass bleaching event in 2016. The scan used to create this model was taken in 2022. Some of the flat table corals are now regrowing, but it's thought the next time a similar event happens, they'll be wiped out completely. Reefs recover, but it can take many years and will happen only if water temperatures allow. As the planet warms, an increasing number of ecosystems are likely to become threatened. The more rapid the warming is, the less likely it is that nature will be able to adapt. If that warming goes beyond 1.5 degrees Celsius, it's thought that climate change will become the biggest contributor to biodiversity loss. The sun is the most important energy source for life on Earth and is fundamental to its weather and climate. The amount of energy we receive from the sun varies naturally over time. So could this variation be contributing to our current rapidly rising global temperatures? Let's take a look at the science and find out. Since the 1970s, satellites have been used to provide accurate live monitoring of the sun's energy, but clever techniques using ice cores, for example, give us information about the sun's activity for thousands of years back through history. This shows us that the sun's activity cycles over time, repeating about every 11 years. At its peak, there's an increase in sunspots and solar flares, with spectacular aurora displays in polar regions. This graph shows us that while solar activity peaks and troughs, the planet has continued to warm regardless of this cycle. Extended periods of low sunspot activity can help explain extended cold periods in some regions, such as the Little Ice Age in the late 1600s. But scientists agree that recent trends in global average temperature rise are much more widespread across the globe and cannot be explained by this 11-year cycle. In fact, recent solar cycles have actually shown a lowering in activity, suggesting that rather than causing the recent warming, it would instead be a factor for cooling. We may even be heading for what scientists call a grand minimum of solar activity. But studies have shown that while this might cool the planet as much as 0.3 degrees Celsius, this would, at best, slow down but not reverse human-caused global warming. A much more dramatic effect on the global climate is caused by the cycle of the Earth's rotational axis and orbital path around the Sun, causing the climate to slowly change over thousands of years. In fact, it's sufficient to push the Earth in and out of glacial periods when ice sheets cover large portions of the planet. The last glacial period finished around 12,000 years ago, and currently the orbital cycles should be causing the Earth to cool again very slowly over thousands of years. This is the opposite of the planet's current rapid temperature rise observed over a much shorter time. So we know that neither the planet's position relative to the Sun nor the solar energy cycles are responsible for the rapid warming of the Earth we see today. Welcome to Climate Station. Using interactive gaming technology, we can explore how our planet's climate works, see how it's changing, and what could happen in the future. Let's start in 1901 and run through the years to the present day. The pins show the difference in temperature relative to the middle of the 20th century. Blue pins are cooler, red pins are warmer. The longer the pins, the greater the difference. Cooler blue areas gradually disappear, and then the warmer red pins take over as the planet warms up. You can see how the warming has accelerated, particularly in recent years, and some areas have warmed more than others, especially the Arctic. We can select any point on the planet to go into more detail, so let's pick a location in the Arctic, Svalbard. The graph on the right shows that if you happen to live there, you'll have seen the temperature rise by over 3 degrees since the middle of the 20th century, and this has had a dramatic effect on the glaciers there. Using photogrammetry from an aerial survey in the 1930s, for the first time, we can see exactly how much ice coverage has been lost from this vast 500 square kilometer area. This shows how the glaciers were in 1936. And this is what they're like now. The red areas highlight how much ice has melted away. The melted water flows into the ocean and contributes to global sea level rise. This graph shows how much the level has risen over time. It's increased by 7 centimeters in just the last 20 years. We can also explore many other important indicators of climate change. We can look at the rise in atmospheric CO2 compared with the global temperature. Advances in technology allow us to build up a more complete picture. Since the 1950s, we've been able to track the rise in ocean heat. More recently, satellites have allowed us to measure the amount of sea ice and the loss of ice sheets in Greenland and Antarctica. We know we must cut our greenhouse gas emissions to solve this problem, but what are the expected consequences of climate change? Let's look into where we're heading. IPCC climate models show us a range of possible outcomes. This is one of these projections, what's called the medium scenario, where we're currently heading and our best estimate for the end of this century. Based on current rates of greenhouse gas accumulation, global temperatures will continue to rise and the world will become a very different place. By 2100, we will reach 2.8 degrees of warming, a long way from our 1.5 degree target. Heat waves, droughts, and heavy precipitation will become more frequent and intense. Tropical cyclones are more likely to generate devastation on the scale of Hurricane Dorian, as shown here. The consequences will affect everyone. But it doesn't have to be like this. We've already come a long way and rapidly adopted green energy technologies. About 15 years ago, climate research indicated 4 to 5 degrees of warming was possible by 2100. So, let's switch to the IPCC's very low scenario, where we act fast and at scale, lowering our emissions to net zero by 2050. As you can see, we can still keep 1.5 alive and avoid the very worst effects of climate change. This requires a change in every part of our economy and society. A drastic reduction in emissions from transport, buildings, industry, agriculture, and energy production. We need to go further and faster and to commit to action. Together, we can safeguard our future.